title of my talk is The Search for Extraterrestrial Life, a 21st Century Perspective. My name is MIllam. I have a PhD in theoretical chemistry from Rice University. Let's see, why is this not advancing? Anyways, so most people have never heard of theoretical chemistry, so I define it here as it involves the development and use of computer programs to apply quantum mechanics to problems in chemistry. So I have a strong background in quantum mechanics as well as in chemistry. I currently work for a company called SemiChem. I'm also a reason to believe apologist and a member of the RTB scholar community. Now, before I go on, I just want to go ahead and introduce two quick rules. One is I love questions. So if someone has a question, please just shout it out, raise your hand, whatever it takes, get my attention. I hope Kevin will kind of keep monitoring, and maybe if I don't catch someone, hopefully he'll bring that to my attention. So again, please ask your questions. When you have them, I will stop and answer them. Questions are what make a good talk a good talk. And the second thing is I love handouts. Now, normally I would be speaking to you in person and I would provide a print copy of these slides for you to have while you're listening to my talk. Unfortunately, I'm not in person, so I can't do that. So instead, I will send Kevin a copy of this PowerPoint file plus another Word document that gives a lot more details than I can fit in my talk. And then he can then share with the chapter. So, again, I want to leave people with resources, that they can have in their hands to, have passed when I give my talk. All right. The search for extraterrestrial intelligence SETI. I'm sure everyone here has heard of it. Most of you have probably seen the movie Contact shown here. Now, my talk, SETI is looking specifically for intelligences, but I kind of generalize this talk to talking about life out there, not just strictly intelligent life. Kind of as a quick overview, so I'll begin by talking about how SETI started in the 1960s and how they understood the universe then, and then looking at what do we know now that they didn't know then. Talk a little about the Great Silence and the Fermi paradox. So what does it mean that we have not actually detected alien civilizations at this point? I'll talk about next about revaluing the Drake equation, just looking at, as we have discovered planets out there, what insights does that give us about this question of life out there? And lastly, I'll focus a little on the philosophical and theological implications that come out of what we've been finding, or in some cases, what we have not been finding as we look for life out there. Okay, so why is this topic so important? I mean, I think it's important because it asks some of the most fundamental basic questions that people can ask. One is our planet cosmically average? Known as the Copernican Principle. Is Earth just a dime a dozen, or is Earth special? Known as the rare Earth hypothesis. But then also the secondary question, does life arise naturally by purely natural processes, or is it life the work of the handy of a creator? Again, these are very deep questions, and one that we can now have more science to back up our answers. I'm probably going to focus mainly on the first pair of questions. Is Earth special or is it not? As I go through this course of the talk. But again, these are deep questions. That's why so many people are interested in this question, because it has huge implications for our life here. Now I'll be talking a little bit about life, and kind of in the background of our thinking. I want people to think in terms of 4 levels of life complexity. So rather than just thinking of life as a whole. So starting off at level 1 would be simple life, microbes, bacteria, viruses, that kind of stuff. Level 2 would be advanced life, like you'd find at a farm or a zoo, that kind of life. And then the third category would be advanced intelligent life. That would be us. And then category 4 is advanced life that's capable of interstellar communication. We finally reached that category in the 1960s when we developed that technology. But SETI is specifically looking for that 4th category, intelligent life capable of communicating, but at the same time, again, I'm generalizing, to other kinds of life. And so when we talk about what is needed to have life on a planet, we need to ask for what type of life. Very simple life has very broad requirements, but the more advanced the life, the very tighter the requirements to have life existing there. All right. Okay, so I already introduced SETI, the search for extraterrestrial intelligence. Give a quick brief history. So in 1959, Cocconi and Morris published the first paper on the principles of interstellar communication. So using radio waves and building radio wave detectors to be able to potentially pick up or even broadcast messages through space. In 1960, someone named Frank Drake initiated what's called Project Ozma, where he just focused a radio telescope at two nearby stars, Epsilon Eridani and Tau Ceti, and simply listened to see if he could pick up on a interstellar channel. That's the true beginning of SETI. The next year, 1961, they had the first SETI conference where 10 people sat around and were talking about these concepts. Is there life out there? Is it intelligent? Can we, detect it? And Frank Drake introduced something called the Drake equation, which I'll talk quite a bit about. And since that time, so SETI in 1960 was started very primitive, just listen to a radio telescope. But over that time, they've become very sophisticated. For example, they have Project Meta, where you can look at 1 million different frequencies at the same time. Project Beta, which is 1 billion frequencies at the same time. Project Serendip, SETI at Home, Project Phoenix, and currently their most advanced project is something called Breakthrough Listen. So again, what they started very simple. This is a very sophisticated, very technologically savvy enterprise using the latest in technology to be able to, search for possible alien signals. Okay, so the Drake equation was introduced in 1961, and so it has these small conference with only 10 people. Carl Sagan is one that everyone would recognize was there, and he was trying to ask questions. Okay, so what factors affect whether life might arise? And so basically, there's 400 billion stars in our galaxy, and if you try to look at each star individually, that would take forever. So the whole point of this equation was to try to filter it, to narrow it down to which stars are going to be the best candidates for having intelligent life. And so basically, he introduced this equation. So n being the number of intelligent civilizations that we might actually be able to contact as a product of these 7 factors. The first is the rate of star formation. Then FP is the fraction of those stars that have actual planets. NE is the number of Earth-like planets within that solar system. And then the last 4 are the biological questions, on how many of these does life actually arise, FIs, how many of those actually give rise to an intelligence civilization. FC is how many of those become communicating. And then lastly is L, the lifetime. So, even if an intelligent civilization arises, it might destroy itself and therefore not be able to communicate with us. I just like to use a slightly different version of this equation. Where we start with all possible stars, and then, and so basically the whole concept here is you start with all stars, and you're simply winning away stars that are less likely to produce intelligent civilization. That's the whole concept here. So you're starting with every star has a planet and it's Earth-like, and then as we learn more, we can start dismissing some. If they have the wrong kind of star, we don't need to look there. So that would help them to focus, their search by eliminating those stars that would not be good candidates. But at the same time, they also use it to try to estimate how many civilizations they might actually be attacked. I mean, because if n was extremely small, then there'd be little point in the exercise. But if n is large, then they have a good chance of finding something, hence the use of the equation. Okay, so we see here are just some estimates that people have given. The first two, one comes from Frank Drake in 1965, and the second from Carl Sagan in 1966. So these are very early SETI estimates, and Frank Drake predicted between 1,000 and 15,000 intelligent civilizations that could be detected out there. Carl Sagan was the most optimistic of any, predicting we might find 1 million intelligent civilizations in our galaxy alone. The remaining three columns represent just three sources I was able to find in 1966, to kind of give a more up-to-date thinking on SETI. And, we still see very optimistic results. So people think, the chances are not that much less than they did back in the 1960s. Okay, so now if these estimates are true, so based on Frank Drake's estimate, the nearest civilization, assuming they're distributed evenly, should only be between 775 and 2,000 light years away. And if Carl Sagan's very, very optimistic estimate of 1 million civilizations, the nearest one should be only 200 light years away. So, the point is, given this perspective, we should be able to find these civilizations very easily and communicate with them. All right, so just to kind of help again put this 1960 SETI perspective, I have a couple quotes. Frank Drake wrote, "At this very minute, with almost absolute certainty, radio waves sent forth by other intelligent civilizations are falling on the Earth." And then kind of as a justification, I could see no reason to think that mankind was the only example of civilization unique in the universe. And again, that's the Copernican Principle notion that he's appealing to, which is a philosophical notion, not a scientific notion, ultimately, that life is common, that there's nothing special about us here. And if that's true, if we're not special and there's life here, then life should certainly be everywhere. Carl Sagan was no less optimistic. Given sufficient time and environment which is not entirely static, the evolution of complex organism is, in this view, inevitable. The finding of even relatively simple life on Mars or other planets in our solar system would tend to confirm that hypothesis. Then in 1992, in a joint statement with Frank Drake, he wrote, "There can be little doubt that civilizations more advanced than Earth exist elsewhere in the universe." Okay, so this is what was predicted in the 1960s, but how does that stand up to scrutiny today? So to go on with a little more from SETI. So the early SETI studies, again, there's many different studies and many different research projects. This first one, Project Meta, which finished its first 5 years in 1993, they found 37 possible candidate signals and then winnowed it down to kind of the top 5, which are shown here. And yet, for the most part, we can be confident these are not actual extraterrestrial civilizations. There's probably terrestrial contamination. So radio waves are great for communicating with stars, but at the same time, we use radio here down on Earth, and it's easy for signals to interfere with measurement and appear to be a foreign signal. Another famous signal that people like to mention is the 1977 WOW signal, which remains the best candidate for an alien radio signal. And so basically you see in this graphic, so you have this computerized printout rolling out, and a scientist astronomer was reviewing it, and he saw something very astonishing, and he wrote "wow" by it. Now, follow-up searches, however, have found nothing. So, we don't know what this was. Multiple theories have been put forward to explain. No one, has completely resolved it. But at this point, again, not overly likely to be an alien civilization. So one signal that stands out in 60 years, and it's, not in any way confirmed to be from an alien civilization. So you may have heard this recently, Oumuamua or Oumuamua, the first interstellar object passing through our solar system. That certainly kicked up a lot of interest. Kind of a comet-shaped, cigar-shaped comet-like object. And so some people have pounced on this and claimed it was an actual alien spacecraft. However, astronomers are quite adamant that this is just a natural object. So, at this point, a lot of people are really hoping to see something. Even more exciting is in December 18th, 2020, so that's only a couple of years ago, the 210-foot Parkes radio telescope received a signal coming from nearby Proxima Centauri. So Proxima Centauri is the nearest star system star to us, and it's known to have at least 2 exoplanets. And so, that got people excited. Do we have aliens nearby? Well, the answer is probably not. While investigation's ongoing, they're probably more likely a terrestrial source rather than an extraterrestrial one. So much to the disappointment of SETI, they have not found any confirmed alien civilizations. Now, I want to start reviewing, kind of put the SETI findings in perspective, what they have found, what they have not found. And to do that, I want to introduce something called the Kardashev scale of technology, because as a civilization becomes more technologically advanced, they have more energy they could direct into broadcasting a signal, and the stronger the signal, the farther away that we can detect them. And so, how well we can pick up a possible alien signal depends on their level of technology. So a type 1 civilization called a planetary civilization can use all the energy of its parent star falling on the surface of the planet. While a type 2 civilization can use all the energy of the entire planetary system, not just the light reaching the planet, but all the light coming off from the sun, that level of energy. And a type 3 would be a galactic civilization, one that can control energy on the scale of the entire galaxy. And just so we don't get too proud of ourselves, on this scale, we're a type 0.7. So we're not even up to a type 1 civilization. Okay, so here is I really like this graph, and I'm going to go through it because I think it's so important and revealing. But this is from Scientific American 2,000 years ago. I mean, 20 years ago in the year 2000, giving an estimate on what SETI has done so far in terms of their search. So you see these. So the horizontal axis. That is the distance from the Earth, and it's on a logarithmic scale. So this first white line here is the extent of the Milky Way galaxy. So everything left of that is in our galaxy. Next line is the extent of our local group of galaxies. And the vertical scale is the signal strength, the power being put into it. So this absolute bottom edge would be Earth level radio leakage. So for example, when television was first introduced in the 1940s, a small amount of that the radio waves would leak out into space. So for example, I Love Lucy is now being broadcast 50 light years from here, but very weakly. This first line would be represent our current level of technology, the Arecibo telescope, which unfortunately just recently fell apart. And that's the level, a civilization at our level of technology broadcasting at this level of power. The next line is for a more advanced type 1 civilization. And then this upper line would be for a truly advanced type 2 civilization. So you can obviously see that type 2 civilization we could potentially detect, way outside even our galaxy, where type 1, we can't detect nearly as far away. And so the degree that SETI has searched these different possibilities is shown in red. Areas that they've really fully searched, so they can have some degree of confidence that if there was something there, they would have picked it up. And then, but there's this large black area, which is areas where the technology simply does not permit them to effectively search. And so we really have no idea what we find. And these colored bands represent areas where we've done partial searches, but the work is still ongoing. So yeah, I think this is really a great graphic to really understand, what we have found versus what we still have left to look for. And just to kind of put these numbers in perspective, this yellow line here, that represents partial searches where we can mostly rule out the possibility of extraterrestrial civilization with technology equal to our own. And then this red line is for type 1 civilization, much more advanced, have stronger signals. We can pretty much rule them out for much of the scope of the galaxy. Again, I think it gives a little more visual perspective on just how far the search has gone, or we can now start. We can't eliminate the possibility of civilizations altogether, but we can, in a sense, put an upper limit. We can put some boundaries, start putting some boundaries on what might be out there. Okay, so now we have introduced the great silence. I'm sure everyone loves Calvin Hobbes, and I love this quote. Sometimes I think the surest sign that intelligent life exists elsewhere in the universe is that none of it has tried to contact us. And I'm sure at days like, especially, reading some of the pessimistic stories in the newspaper, it's easy to kind of appreciate that wisdom there. But yeah, the great sign, the fact that we have not found any inclusive alien civilization despite 60 years of searching, despite multiple projects. What does that all mean? That's what I'm going to focus on next. Okay, so just to conclude, okay, so first, no definite alien signals have been detected. Only a few possible weak signals but are more likely to be naturally some other cause. UFOs do not represent extraterrestrial visitation. This could be a whole talk in itself, and I could give that talk in the future if people are interested. But there's widespread agreement that UFOs do not represent extraterrestrial visitation. And the third, our solar system appears untouched. If aliens ever came through our solar system, they would probably be mining our asteroids for important resources, but we have no evidence of anything like that. So we have no reason to believe that aliens have ever been in our solar system. So why these observations do not rule out the possibility of alien life, they do put an upper bound on their prevalence. So some of the most, the most optimistic projections made by Sagan and Frank Drake, I think we can start ruling those out, although we can't rule out all possibilities at this point. Okay, so now given that negative conclusion, you think SETI would be giving up, nothing to find, but in fact, SETI supporters are even more enthusiastic than ever. And some points of evidence that lead them to be optimistic are, one is discovery of extrasolar planets. I'm going to focus on that a lot here, but the fact is there are literally billions and billions of planets out there, probably one planet per star in our galaxy. So that's on the order of 400 billion planets that could potentially be searched. So there's a lot left to search that we've barely even scratched the surface. But life at hydrothermal vents. So as you see in this graphic, life can exist in extremely harsh conditions, a couple kilometers beneath the surface of the ocean, where you think it would not be able to exist. So if it can exist there, then there's many possible situations where life could arise on a planet. Extremophiles, so those are organisms, usually microscopic organisms, can live in extremely harsh environments, in strong acids, strong bases, high temperatures, radiation, places you'd expect that nothing would be able to live. There are some life forms that can actually live there. And that increases where at least the simplest life forms could possibly exist. Others have proposed life on moons. So some of the moons of Jupiter are big enough that they're basically as big as terrestrial planets like Earth. and some have, an icy top with water underneath. So, some have proposed that there could be life even on the moons, Jupiter or Saturn in our own solar system. The origin of life experiment, some see the origin of life as being very easy, in which case they would expect life to be common. And then red dwarf stars. Red dwarf stars are the most common type of stars out there, representing 76% of all stars. And if they have planets, that represents a huge possibility. So we no longer have to rely on just yellow stars like our own. Maybe red dwarf stars, could host life as well. Okay, so where to go from here? Kind of the one key point is that so far I've been focusing on negative evidence. We do not find, but as the famous quote, the absence of evidence is not necessarily the evidence of absence. Simply because we cannot detect alien civilizations does not mean that it's necessarily not out there. So I want to now switch gears and look at positive lines of evidence compelling to consider the case that extraterrestrial civilizations are unlikely, and actually try to demonstrate design in our own solar system. That we aren't an average, common, mediocre planet. That there is actually something special about us. So this is a picture here is of Enrico Fermi, famous Italian physicist. 1950, he was having a lunchtime discussion with some of his friends. They're talking about extraterrestrial civilizations, interplanetary travel, and then suddenly he blurted out a question, so where is everybody? In other words, if aliens were as common as was presumed at that time, then not only would they exist, but they would have spread throughout the galaxy and would be knocking on our door. But the fact is, we have no evidence, even in the 1950s, that aliens have ever been here on Earth. And so that's a paradox. So either the aliens are not out there, or they're out there, but we can't discover them. But there's a paradox. Something must be wrong with that logic. So, and that became known as the Fermi paradox. To kind of put it in more formal terms, it's the apparent contradiction between the lack of evidence for and the high probability estimates for the existence of extraterrestrial civilizations. So step by step, there are billions of stars in the galaxy, and many of these are billions of years older than our solar system. Many of these stars are expected to have Earth-like planets, and if Earth is typical, some of them may have developed intelligent life. Some of those civilizations may have developed interstellar travel, a step that Earth is currently investigating. And even at the slow pace currently envisioned, interstellar travel, the Milky Way galaxy could be completely traversed in a few million years. Now, that's a very startling conclusion. Space is vast, even our galaxy, and yet one civilization could potentially spread throughout a galaxy in as little as a few million years. So if all of those statements are true, then we'd expect to see clear evidence of aliens visiting us here on Earth, and yet we have not detected either aliens, their robotic probes, or even any extraterrestrial civilization. So somewhere this logic has to fall down, and the question is, what's wrong? What's the failed assumptions? So just a quick look at intergalactic colonization and the Fermi paradox. So we know that, as far as we know, spacecraft cannot travel faster than the speed of light, and the speed of light, as fast as it is, that is the distances between stars. So getting even to the nearest star is going to be slow and difficult. Yet, even foreseeable technology, we could estimate that a single civilization could spread throughout the galaxy in as little as a few million years, or at most 50 million years. And again, that's very brief compared to the age of the universe, or even the age of our galaxy. Non-biological robots could spread even faster, and yet we haven't seen any of those. Here's kind of a quick graphic. So if you just try to model this, assuming that there's an average of 10 light years between a planet that's worth colonizing, ships can travel at 10% the speed of light. In the period of 400 years between starting a colony and sending out new colonies, you could spread throughout the entire galaxy in 3.75 million years. So you have this exponential growth. So you see up here, you have planets sending out 2 colonies, and 10 steps later, you see you have a whole bunch of colonies, and then spreaders, farther and farther. You have this exponential growth, and so that's kind of the argument being made is that that this could happen very, very rapidly as aliens become spread out. So there's great reason why an alien civilization would want to do that. There's a huge payoff to be the first to colonize. You get lots of resources, no opposition. Technology will continue to advance, so the speed of colonization will actually get faster and faster. And so that few million years is actually an overestimate, probably. You could even have self-replicating robots that would speed throughout the galaxy faster than biological beings. So the question is, does that prove that alien civilizations are not out there? That the fact that we have not observed them here, and of course, that's very much an issue of debate. Many people will not agree to that conclusion. There's a really wonderful book. Anyone who's interested in the subject, I really highly recommend it. Stephen Webb, Where is Everybody? So he gives 50 different responses to this Fermi paradox. And he breaks those responses down into 3 basic classes. The first class is they are here, that the aliens actually have gotten out to where we live. So you have some things like the zoo scenario, or if you're a Star Trek fan, you call it the prime directive. So they're here, but they're intentionally hiding themselves. Or maybe there's what's called the interdict scenario. You're halfway between 2 great civilizations, or neither is really able to project control here. Second class is they exist but have not communicated. So for example, maybe interstellar travel is really too difficult. Maybe we were overestimating how we might get to other stars. Or maybe they're sending out signals and we just haven't listened long enough. Or they're calling and we simply do not recognize the signal. So again, as we've shown, there's a lot of possibilities out there that have not been fully explored. So maybe there are signals and we just haven't found them. Or maybe they simply stay home. They just decide it's not worth it to travel anymore. And the third category is they do not exist. That's kind of the natural reading of the Fermi paradox. So perhaps habitable are rare, that we're actually special, that we won the cosmic lottery in having the right planet. Continuously habitable zones are narrow. The conditions needed for life on a planet are maybe much narrower than we estimate. Planetary system is a dangerous place. There's a lot of things like a giant asteroid could wipe out life on Earth like it did for the dinosaurs. Jupiters are rare. Turns out our Jupiter actually helped protect us from asteroids that could wipe us out. Maybe other solar systems don't have the equivalent. Our moon is unique, or nearly unique, and that has enabled us to have life here. Maybe other planets don't have that, and therefore sterile. Maybe life genesis is rare. So again, there's many different takes on the Fermi paradox. Some having alien life out there, some rejecting it. And again, very well written book. If anyone is interested, this is a great place to start in looking at this question. Okay, and just kind of as a perspective, in the early days, SETI was very primitive, looked exclusively at radio waves, but SETI has advanced leaps and bounds in the last 60 years. What they're capable to do is far greater than they could at the beginning. So multi-frequency searches, they have much greater sensitivity. They're also looking in optical and infrared frequencies, not just radio waves, looking at wide sky as well as targeted searches. And they're no longer just depend on active signals. So the whole concept of SETI was, if someone's trying to broadcast to us, can I pick that up? But what if they're not broadcasting, or they're not broadcasting in the way that we're expecting? Called intentional broadcasting. So is there a way that we can pick it up that does not depend on them having to do anything? So just, how do we actually detect an alien civilization? And again, if we're in the traditional approach, we're looking for active, that is intentional broadcast. They may fail because we may be not looking at the right frequency. We can only guess what frequency they might broadcast. We may not be looking at the right time. We use the wrong search strategy. Aliens just might not be broadcasting at all or dead, or the signal is simply too weak to detect. So there's a lot of ways that aliens could be out there, but we simply don't detect them. So kind of a different strategy that's been building up in the last few decades is looking for indirect passive detection, things that don't depend on the aliens trying to do something, trying to communicate. So one of those is what are called biosignature gas. So when we look at a planet, as it passes in front of a star, we can get some light passing through the atmosphere, and we can detect gases in that atmosphere potentially. It's very difficult to do, but it can be done. We can learn something about what's happening on that planet, and some of those gases could indicate that life is active on the planet. A second detection method is infrared. Large-scale technology generates heat, and we should see more infrared light given off than we expect if there's an advanced civilization. So that's an indirect way we can pick them up. Transit dimming. So one of our main methods for detecting exoplanets, you have a planet, imagine here, and you have this exoplanet orbiting around it. As it comes in front of the star, it can block out a little bit of light. And that's how we can know an exoplanet there. But as an alien civilization advances and they need more energy, they can put up these huge kind of solar sails around their star that will collect energy. And if they do that, that can be potentially detected, because that will block out light in the way a planet would. So we could, in a sense, detect their technology that way. And so based on this, I would conclude that an alien civilization with technology just barely beyond our own, maybe 100 years at most, would be able to know that we are here, even if we don't send out any messages. And in 100 years from now, we'll be able to know with a fair degree of certainty what planets could at least potentially have alien civilizations or not, but it's completely independent of them trying to broadcast to us. So just a quick statement on biosignature gases. These are gases produced by living organisms. You have a lot of living organisms that can produce a lot of gas that can be potentially detected remotely, that give an indicator but not proof of life. So, for example, if you looked at the spectrum of Earth, you see a lot of oxygen and ozone. That oxygen and ozone is put out by plants and other organisms. Of course, water is necessary for life, and then methane is also a byproduct of life. In fact, we have both oxygen and methane present at the same time. Really would be a huge signal that there's life here. So just kind of, here's a quick graphic. Here's the spectra for Earth. We can see things like the water and oxygen and methane. Here's an example of Titan, one of the moons of Neptune, which has just methane in the atmosphere. So kind of see the contrast between those two different graphs. All right, so now kind of just refocus things and reassess the Drake equation. So basically, Drake equation expressed how they were understanding how the universe worked back in the 1960s, in which case they were very optimistic about finding alien civilizations. But now, that we've started finding exoplanets, planets orbiting stars than our own, we can now more directly assess that rather than assuming we have more evidence that we can actually work with. And so, the Drake equation can be divided into two parts. One dealing with the astronomical factors, that's the first 3-4 terms, and the last 4 dealing with the biological side. So I'm going to just focus on the astronomical factors. biological factors being very speculative. So as of January, we have 4,940 exoplanets have been cataloged. So we now have a sample of planets that we can start to work with. How does that sample compare to what we assumed about exoplanets, what we assumed we would find? Okay, here's just the dividing up of the equation. Okay, so as we reassess the terms, the first one is, what is a suitable star? So in the original Drake equation, that term was not even present. Any star is equal to any other star. But as we've learned more, it turned out the type of star is actually very important. We orbit a yellow star, and moreover, it's a single star. It's not two or three stars, but just one. But there's a number of different properties of the star that come into play. One is its overall mass, which determines its temperature. Whether there's one or two, or even two or three stars in the system, things like solar activity flaring. If there's a lot of solar activity, it can strip off atmospheres from planets, and since atmospheres are necessary for life, that would definitely be bad. The age of the star, metallicity, which would be the presence of elements heavier than hydrogen or helium, stuff that you need to build planets out of. So it turns out that the star is very important for determining whether or not life is even possible in that system. This is kind of just a quick table. I'm going to just go through it very rapidly, but all stars, main sequence stars, so not black holes and stuff like that, go into one of 7 different categories by temperature. So we orbit a yellow star, which is called a G-type star, which is kind of middle of the road. Red stars, or M stars, are the very lowest mass stars, down to potentially 8% the mass of our sun. And then at the bottom are the very bright, hot, massive stars, the O. And you can see here by mass, dim stars last a long time. So red dwarf stars could potentially live 70 trillion years, whereas our stars estimated to will live about 10 billion years. You see that red dwarf stars are about 76% of all stars, which is why astronomers they're very popular astronomers, because there's just a lot of them out there. Yellow stars like our own, about 7.6%. And the massive ones there are very few of them out there. All right, so what does star type and planetary habitability have to do with planetary habitability? One is you can have multi-star systems called Tatooine planets. So if anyone's watched Star Wars, you remember Luke Skywalker on his planet Tatooine, and he sees 2 stars, 2 suns up in the sky. So that would be an example of a multi-star planet in a multi-star system. And so about half of all stars have at least 2 or more stars in the system. And that has a number of problems for planets in there. It doesn't, some could potentially support life, but most multi-star systems would be very poor for life. Have very large, massive stars more massive than our sun. They're very bright, but then that means they burn out too rapidly. They just have short lifetimes, and so those stars are very unlikely to be habitable. That leads us to red dwarfs. So these were not considered back in 1960 because they hadn't been detected yet. They're very popular today because when you're looking for exoplanets, the smaller the star, the easier it is to find a planet around it. It has to do with technology. And also red dwarf stars are very common. And so most of the exoplanets we're discovering are around red dwarf stars. Those are the ones gaining all of the media attention. But the question is, can red dwarf stars really support habitable planets? And likely no. One is habitable zone is very narrow. So red dwarf star, they're much smaller, which means everything has to pull in a lot closer. So planets would be very close to the star, but that means you have something that introduces two problems. One is what's called tidal locking. So, tidal locking is the same situation we have with the moon, where we only see one face of the moon, because the tidal forces, the gravitational interaction, keeps it, slows it down so that only one face always faces us. So in the case of a planet tidally locked to a star, then one side gets all of the heat and therefore becomes enormously hot, but then the side opposite of that gets no heat and becomes very cool unless you have a very thick atmosphere to direct the heat. And so that would make planets like that very difficult to be habitable. They may experience severe solar flaring, and there are stellar winds. They can strip away atmospheres from planets. And again, atmospheres are very important for life. And so red dwarf stars have a lot more flaring. And also the planets being a lot closer means they're going to be hit a lot harder. And so just based on these two factors, my conclusion is that only single stars and sun-like stars, that is class G, like our own sun, or maybe orange stars, which are just a little bit below that, offer the best chance of habitable planets. So again, like Goldilocks, you don't want anything that's too hot or too cold. You need something in between. This is kind of a interesting article I came up with in 2019. Talked about how red dwarf stars in their early phase are very active, setting a lot of radiation, and that can strip away an atmosphere from the nearby planets. And kind of the conclusion is life forming in red dwarf star systems appear to be less likely than previously believed. So that, there's been a lot of hoopla around red dwarf stars in the last decade, and yet it's kind of throwing a lot of cold water on it. Okay, next is what is a suitable planet? So, back in 1960, they assumed that most solar systems would be basically mirrors of our own, in which case Earth is clearly habitable. So there should be at least one habitable planet, one planet orbiting at the right distance from the sun to stay warm. But some thought even maybe three, like Venus and Mars, are close to that region of getting enough warmth. So basically, SETI assumed that life requires water, so you have to have liquid surface water and prebiotic chemicals. That's all you needed for life. And that would mean a small rocky planet, not giant gas giants like Jupiter. And you want the planet located in the water habitable zone, that is a distance where it's not too far away from the sun, so it's too cold or too close. And they assume that most solar systems would strongly resemble their own, in which case, if we have one habitable planet here, then that would assume, predict that we'd have a lot of habitable planets out there. But now we can start testing that idea. And I mentioned the water habitable zone. I just want to kind of reinforce that. So again, how far away a planet is from the star determines how much energy heat is receiving from the star. And if it's too close in, like Mercury is or Venus is in our own solar system, it's going to get too hot. It's going to boil over. Life can exist there. But if it's too far away, like Mars and Jupiter and Saturn, it's not going to get enough heat, and it's going to be frozen. And so this Goldilocks zone, this narrow band in which the planet can get enough heat but not too much heat, so it can be just at optimal temperatures. Temperature in the right range, you can have liquid surface water, which is necessary for life. One thing that's been interesting is as we've been looking at other solar systems, as we're discovering these planets, rather than finding clones of our own system, we're seeing all kinds of things we never expected to find. We see a lot of things that diverge dramatically from our own solar system. One is planets around pulsars. So pulsars are basically neutron stars, and that have ended their life and would have destroyed any planets around them, and yet some have managed to have planets. Clearly, life would not be expected there, but hot Jupiters. That was the first true exoplanet that we discovered. So imagine the giant Jupiter gas planet in our own solar system but rather than being orbiting way out there, being so close to the star, they can orbit the star in 4 days or less. I mean, just way in there, which means that it's ultra hot. It's right next to the sun. But the problem is, if Jupiter is that far in, it's going to destroy any, terrestrial planets like our own. And so, such solar systems would be very hostile to life. Super Earth and mini Neptune, this is the one positive potentially discovery for SETI. So in our own solar system, we have 4 terrestrial planets, these Earth-like planets. That'd be Mercury, Venus, Earth, and Mars. And then the next biggest planets would be Neptune and Uranus. And there's this huge gap between those. And we're discovering some planets that kind of fit in that gap, that are bigger than Earth, but smaller than Neptune. And so we don't have any solar system examples of what that's going to work like. So some people think these may be habitable or even more habitable than Earth, but that remains to be seen. We see multi-star worlds. I've already talked about that. Styrofoam planets, kind of gaseous planets like Saturn, but even more puffed up, more spread out. Diamond planets, they have enough carbon that they might have actual large quantities of diamond forming in the planet. Hot Earth or lava planets. An Earth-like terrestrial planet that's orbiting so close to a star that its surface can be covered with molten lava. Definitely not a place you want to visit. And even rogue planets, planets that have been kicked out of the solar system and are roaming free, completely independent of a star. So some people even think there may be 1 to 10 rogue planets for every real planet. So there could be on the order of, unlike what was assumed in the 1960s, most solar systems are not like our own. They're not simply clones of our own. And that really has a strong impact on our expectations. Here's one important graphic. To have life, you really need to be, this is organized by size. You have subterran, so smaller than Earth, Terran to be Earth-like size, superterran to be bigger than Earth, but smaller than Neptune. Neptunes would be these giant ice balls, and Jovans would be like Jupiter. So you first of all need planets in the Terran and possibly super-Terran category. But at the same time, you need the right temperature. The planet needs to be orbiting at the right distance. So red means it's too close in, which means it's too hot. Blue means it's too far out, so it's too cold. So you want these yellow be in the right temperature zone. And you notice, out of the 4,000 or so planets that were included in this graph, using only 2 size categories and only the yellow, that greatly, only a few planets satisfy both of those criteria. So warm Terran, super-Terran planets, only 1.4% of that selection. And I think that's telling. Even using 2 criteria, we're finding Earth is very much in the special category. And if we add more criteria, then we find out Earth is even more special. Okay, so I'm not going to go through all these. You can, you'll have a copy of this presentation to look at afterwards. But again, SETI largely only assumed you need 2 things, and in more recent times they assume only 3 things need to be true. But it turns out a ton of things need to be just right to have habitability. The nature of the atmosphere. You need a planet that's not tightly locked. You need plate tectonics to ensure that you have a magnetic field. You need a carbon-oxygen ratio, the magnesium to silicon ratio that determines what kind of crust you have. You don't want one that's too thick or too thin. The actual tilt. And so, SETI initially assumed you only need to consider the planet, but turned out we also need to look at the entire solar system, not just the individual planet. As we need to look more holistically. So for example, the fact that we have a large moon is part of the reason we've been able to exist here. If we didn't have our moon, we wouldn't be here. The gas giant planets, Jupiter acts as a cosmic guardian, protecting us from impacts. planetary migration. So planets don't stay where they're formed; they can move in, just like the hot Jupiters. And when they do, they can wreck the inner solar system. And so we have a Jupiter that moved in and then drifted slightly back out, and so it's in just the right position. And there's other things like in plane orbit. You need to be in all 9 habitable zones. So just kind of highlighting here the moon. Again, people often think of moon just that, it's very romantic, that beautiful thing in the sky, and yet we often forget that we wouldn't be here without it. So basically, very early in Earth history, a very large Mars-sized boulder hit the Earth in an exceptional and fine-tuned event, stripped away our Earth's early thick atmosphere, which had been like Venus, and we'd be over hot, and took that away. So we got a nice thin atmosphere, increased Earth mass, gave us iron and radioactive elements, which we need for a strong magnetic field, and also increased the Earth's rotation speed. But at the same time, and ongoing, it helps stabilize the Earth's obliquity. So if this represents the plane of the solar system, our planet is tilted at 23.4 degrees relative to vertical. And so without the moon, our axial tilt would be flipping around by a lot, the way it does for Mars. And that would cause huge environmental changes, that would make climate change seem like nothing in comparison. And so we found that, that there's even more evidence that the Earth-Moon system is just precisely designed for us to be here. I mentioned Jupiter earlier. So having a gas giant planet is important because then in 2 ways. One is it strips out a lot of the early comets and asteroids and other material from the solar system, either absorbs it directly or cause them to be tossed out of the solar system, without which Earth would suffer extinction level collisions 1,000 times more frequently than we actually have. So imagine the asteroid that killed off the dinosaurs happening, once every 50,000 years. That would be devastating. And at the same time, it has an ongoing help of deflecting or absorbing comets that may come into the solar system. And for that, it has to be in the right, it has to be massive, it has to not be too close in or too far out. It has to be just right. And then Galactic SETI has never even bothered to really consider this, but where the star is located in the galaxy matters. What type of galaxy matters, what the environment around the galaxy matters. So again, SETI assumed only 2 or 3 things need to be true, and yet we're learning there's dozens and dozens of things that have to be just right for us to be here. So these are just a couple examples. It's good that we're near the galactic rotation distance, so we don't spend a lot of time in the arms, and we stay between that a lot. And the other things, we're not getting hit by supernova or gamma ray bursts, and so on and so forth. And so, so many things that you're right. I love this galaxy. You must be here. That that for us to be here, we couldn't be just anywhere in the galaxy. That that there's really only kind of safe zones. Some places are definitely better than other places to be, and so we're in a just right spot. Okay, so I introduced the Drake equation, and there's a number of criticisms of me. So on one hand, it deserves a lot of praise because in terms of helping focus discussion to think about what's needed to have intelligent life on a planet. In that sense, it's been a wonderful tool. The problem is when people actually try to calculate the number of intelligent communicating civilizations based on that equation, it was never designed for that. And when you do, you get dramatically larger results than reality. And so that is part of the problem, is people are trying to actually calculate the number of potential intelligent civilizations, and that makes it sound like there's a lot of them out there, when in fact that's more problems with the Drake equation. But I won't go through all of these, but again, they use very simple criteria for life. Basically, you only had to have a planet of the right size, not too big, not too small. It had to be the right distance from the star, not too close in to be too hot or too far out. And then you also need the right star type. But we're learning that's not even sufficient to support microscopic life, much less advanced life. So to improve the direct equation, you have to have a lot more terms, because for advanced civilization, you need a lot of things to be true. Mainly they're focusing on astronomically measurable properties, and yet many other important properties are not measurable easily and yet are relevant. So those are ignored. They need to be updated to include recent discoveries. We're discovering more and more things that have to be true for life. And in large part, SETI has resisted including those, even though we can see and measure them. So effectively, direct equation only expresses where life cannot entirely be ruled out. So in other words, it's the number of places we might look for a civilization, not we might actually find one. And worst of all, the equations predicting are effectively unfalsifiable. Okay, so kind of moving into the last more philosophical question. So, we're really facing, there's two different worldviews at stake here. One is the SETI worldview, which is based on the Copernican Principle, which is basically the notion that the Earth, that we're not a special observer, that we are average, that there's nothing special. The universe is largely uniform, homogeneous. The same physics apply everywhere. There's really nothing to distinguish our solar system from others. So other solar systems should be basically like our own. Carl Sagan expressed this view very succinctly. Who are we? We find that we live on an insignificant planet of a humdrum star lost in a galaxy tucked away in some forgotten corner of the universe in which there are more galaxies than our people. So basically, that's the embodiment of the Copernican Principle. We are just utterly average. There's absolutely nothing special about us. But one thing I appreciate reason to believe is Hugh Ross, and actually looking at some design preferences. You see, back in 1960, there's really only two. But as time has gone by, finding more and more of these design evidences, things that need to be just right. Where again, SETI is really only, even out in 2010, only considering 3, and yet there's literally hundreds out there. And so that notion of design leads to what's called the rare Earth hypothesis, that planetary systems, and galactic regions that are friendly for life are actually very rare, not average, not common. So advanced life required many more just right properties than assumed by SETI. When you include these factors in the Drake equation, the number of predicted civilizations would be extremely small. And this is the opposite of the Copernican Principle. And so that's one author saying. Here's a different author, Robert Ney, author, senior editor of Astronomy Magazine, and he makes this very profound statement. Recent studies in a variety of fields suggest that life must pass through a series of bottlenecks on the road to intelligence. On Earth, a long sequence of improbable events transpired in just the right way to bring forth our existence, as if we had won $1 million lottery 1,000,000 times in a row. Contrary to prevailing belief, maybe we are special. Maybe humanity stands alone on a fertile island in the largely sterile waters of the Galactic Ocean. Now, just see how big of a contrast it is to Carl Sagan's statement that we are just absolutely humdrum and average. Okay, so he lists 11 different considerations of things that could eliminate life, filters that we have to pass for us to be here. I'm not going to go through all these. You need obviously liquid water, you can have the right sun, you have to have the right planet, you need the right atmosphere, magnetic field, you actually need plate tectonics. And then what about the arrival of intelligence? The importance of Jupiter, which I've already talked about, the importance of the moon. You need intelligence, and of course, you need to avoid killing yourself, all of which have been true here on Earth. And when you consider just those 11 factors, not 676 the Ross list, but just these 11, he concludes, but until we discover alien life, it seems more prudent to conclude that we are alone in a vast cosmic ocean, that in one important sense, we ourselves are special, that we go against the Copernican grain, that we're not average. And one thing that's interesting is that he says at the very end of the article that he really hopes he's wrong. In other words, that he wants there to be extraterrestrial aliens to be discovered, and yet looking at the evidence, he is forced to conclude that we are probably alone. And I think that makes his statement all the more profound. And then, of course, I got to end with Guillermo Gonzalez. Some of you may know him. I like his statement when he responds, "My answer to the question, are we alone, almost always catches people off guard. Very likely, yes, we are alone. When one looks at the astronomical data with an open mind, it becomes quite obvious why we have not found any evidence for extraterrestrial life." And he adds, "We should not be asking, are we alone? We should be asking, why are we here?" That's a profound question that I think all of us you should be really thinking on. So just kind of in conclusion, the SETI assumptions, they were optimistic to believe that most sources are like our own. We know that's not true. We can actually see that through our current measurements. The Fermi paradox, the failure to detect aliens sets a strong upper bound on what might be out there, although we can't completely rule out other life. Exoplanets, other systems are not like our own. We're learning more and more how special we are and find the rare Earth hypothesis. Contrary to what was assumed in the 1960s, Earth is neither commonplace nor average. Kind of add, and we better take care of Earth because there are a few other planets remotely like it. So not like Star Trek, where we can just flip over the next solar system and find another beautiful untouched planet. We better take care of this planet. All right, so that's where I'm ending the presentation. This is just a reading list for anyone that ultimately wants to go farther. But